Tell me when you're ready. Okay, ready. Okay. Okay, ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. Chapter 4 is transient heat conduction. Transient means how things changes as function of time, or unsteady heat transfer. There are different categories in this textbook of how these types of problems can be solved. First category was the lumped system approach, and we've already done that. The lumped system approach is where there are no temperature differences inside a body. The equation is very, very simple, but if you use that, you cannot inside a body distinguish temperatures at different positions. They all will have the same temperature. Those category of problems would occur if the thermal resistance of conduction inside a body is much smaller than the convection heat transfer on the outside. A good rule of thumb is about 10 times. So if there is a resistance on the inside is 10 times smaller than the outside, then that is the Biot number, which is 0.1. So that is the criteria that we use. The second part of the work was looking at conduction heat transfer through plane walls, cylinders, and spheres. But one-dimensional, there are equations to be solved. They can be very complicated, but you can also make them much more simple. Okay. Then we've started looking at transient heat conduction in semi-infinite solids. We've said a semi-infinite solid is a body where there must be a plane surface. So that's the first thing. And then the rest of the body must be very large. And very large is always something which is very relative. Obviously, we can say the Earth is large. So if we are interested in the first 2 or 3 meters, how the temperature changes inside the Earth, then we can use the lumped system approach. And with the previous lecture, we've looked at the case where the Earth's surface was now suddenly at -30 for 3 months. Okay, and it takes, after 3 months, the temperature at the depth of about 1.5 meters or 1.8 meters, something like that, would only reach 0 degrees Celsius. So typically at 3 meters and 4 meters, the temperature would still be constant. So the temperature of the body remains constant. So other applications would be maybe a wall like this one. Okay. Now this wall might be 400 or 500 millimeters thick. I don't know. If it's 500 millimeters, it would be a very, very thick one. Again, if we are interested in what happens very, very close to this wall, then we can use the lumped system approach to determine the temperature distribution as a function of depth. However, if this is our wall, we cannot try to get the temperature on the other side. Okay, that would be too deep. So it is all very relative. So today we're going to continue with this work and complete it, I hope. Now with this, we've also derived an equation, typically like that, for very specific boundary conditions. And this boundary condition for this one was specifically if this temperature now suddenly at T equals 0 would change to Ts, while the rest of the temperature in the body remains constant. Okay. And since we can get the temperature gradient, we can also get the heat flux, and that was the equation. Right. So let's continue with the rest of this lecture, or this part of the work. All of you are sitting on a wood bench. Okay. Take your finger and determine the temperature, and then there's also some steel next to you or around you, and also put your finger on that. Okay. Which one is the coldest? Okay. Which one feels the coldest? The steel feels the coldest. Okay. So, yes, you are right. We are in this venue, and the air conditioning system of this building is very sophisticated. And if it works, not always, but if it works very well, then the temperature in this venue for the past 2 or 3 days were relatively constant within about 22 to 23 degrees Celsius. So the temperature of the hood and the steel and everything should be the same. Okay. Now, in winter, if you're in your house and you are bare feet and you walk around and you walk from an area with carpets to an area where there's no carpets, maybe towels, you would say, oh, the towel floor is very, very cold. Okay. And my father typically always believed that. He said, you know, never put towels in your house because it's cold for the winter. Now, that is not absolutely correct because the temperature of the carpet and the towels are exactly the same. But why does it feel cold? Okay. So I'm going to answer that question to you just now with good examples. So the specific part that we're going to do now is an application of the semi-infinite solid, but where we put two semi-infinite solids together so that they touch. Okay. So in terms of temperature as a function of x, what we now have is a semi-infinite solid with this, take note, very, very important, with this plane surface. Okay. And schematically, that is that semi-infinite solid. And it has a temperature TA, and it will have properties of K, rho, and Cp. Okay. And now, that semi-infinite solid touches another one. Okay. So we've got two semi-infinite solids touching each other, but with different temperatures. Okay, the one at temperature TA and the other one TB. And their properties also K, rho, and Cp. But it doesn't mean that the properties must be the same. So therefore, the properties on this side we are going to call A, and the properties on this side B. So the values of K, rho, and Cp are not the same. Right. Okay, so in terms of temperatures, if this is now the scale of temperatures TA and TB, okay, and that would now be for T equals 0. So T equals 0, we put the two semi-infinite solids together. Right, now this temperature was at TA. Okay. Now let's plot TA there. And the temperature is uniform throughout the body. Okay. At B, that is the temperature there, again, throughout the whole body. Okay. Now, what is going to happen when these two bodies touch each other with different temperatures? The one at a higher temperature than the other, so there must be heat transfer between the two. Okay. So the heat transfer must be in that direction. Okay. And the heat transfer, let's call it the heat flux at the surface of A, must be equal to the heat flux at B. Okay. Remember, the heat flux is the heat transfer rate divided by the surface area. Okay, the heat transfer rate in watts and the area obviously in square meters. So the heat flux, the units of the heat flux is the watts per square meter, which is being transferred from the body at a temperature A to a temperature B. Right, so that is at T equals 0. Now, let's look at what is going to happen at a temperature later on, which is again T as a function of X. And again, we've got the two bodies here, like that. Okay. And then at T equal infinite. Okay, so temperature is a function of x. Okay, so 10 seconds, 20 seconds, or 1 minute later, typically the temperature behavior in this at t equal a little bit later, that's TA and TB again. Let's just put it in, TA and TB. Okay. So just finish all your graphs quickly and your sketches and think about it quickly. What do you expect with the temperatures is going to happen? And make a sketch in your notes in terms of what you expect is going to happen. Okay, so after a while, typically what is going to happen with the temperature in this body? What is very important to remember is this temperature here should remain constant, because remember, it is a very large body, because that is what we say, semi-infinite. Okay, and this one is also going to be constant at TB. Okay, like that. But now here close to the surface, we have to get something like that. Okay, and this temperature here is called obviously the surface temperature, and for body A and for body B they should be the same. Okay. Temperature should be the same. Right. Okay. Okay. Then at T equal infinite, then the temperature of this body and that body should balance each other out like that. Okay, do you agree? No, wrong. Okay, if the two bodies are, remember we are talking of large bodies, and as I've said, okay, it is relative. So if you've got two bodies, each with 2 or 3 meters, okay, then yes, after a while, the two temperatures is exactly going to do that. But it is not going to, in terms of the mathematics that we've derived, this is not going to be valid anymore. Because in the boundary conditions for this, we've said that the temperature, when x goes to infinite, remains at Ti. Okay. Okay. So we cannot really do that condition for this. So we must say no. Then the semi-infinite solid assumption not valid anymore. Okay, now if I say assumption, maybe I should have said boundary conditions. The boundary conditions that we've imposed on this problem is not valid anymore, because we've said that the temperature in body A, okay, is a constant, if T goes to infinite and or when T after X goes to infinite. Okay, so that was in the boundary conditions that we've derived. And the same for body B. Okay. So exactly the same for body B. So many people will also look at this and say, but these temperatures actually maybe did something like that before it would reach that position. But what is going to happen actually, which is very interesting, and we're going to derive it just now, is that let's suppose that is T equal 1 minute. Okay. What is it going to be after 10 minutes? Okay. After 10 minutes, it is going to also, this temperature is going to be constant, but now it's going to do something like that. So this temperature is going to remain a constant. It's not going to change. Okay. When we touch two semi-infinite solids, because this temperature and that temperature inside, it remains constant. Okay. And the heat flux is a constant. Okay, so in terms of the heat flux, okay, the heat flux of body A is equal to the heat flux of body B. Okay, so let's do the derivation of it. Okay, and that is the reason why I've written down this equation, because this equation follows from the previous work where if we have the temperature distribution, we can calculate the heat flux on the surface. Okay. So that tells us that K multiplied, the K of body A multiplied by the surface temperature minus the temperature inside divided by the square root of pi alpha and T. Okay. So look at the equation. The surface temperature minus the temperature on the inside is equal to, on the B side, the same thing. Okay. So K multiplied by the surface temperature minus B, the initial temperature, divided by the square root of pi multiplied by alpha, the diffusivity, multiplied by time must be equal to 0. This term must be equal to that term, the two heat fluxes. Okay. And remember, alpha is equal to the diffusivity, which is K divided by rho Cp, if you can't remember what it is. Right. So if we now look at these two equations, are you happy with them? Okay. Okay, there's just one minor problem here, and that is, if we look at this heat flux, okay, the direction of it would be that temperature is higher than that temperature, okay, you see? So the heat flux must be in that direction. So if you don't put in a negative sign here, then the mathematics is not going to be absolutely correct. So you need to put in the negative sign for that. Right. So now you can see many things cancel out. For you it's very, very simple. You can go and do it at home. But what you now can do is you can go and derive the surface temperature. And the surface temperature is going to be, I'm going to write it like this, F, and I'm going to define F to you just now. So F of A multiplied by the initial temperature of A plus F of B multiplied by the temperature of B divided by FA plus FB, where F is equal to the square root of K multiplied by rho multiplied by Cp. Okay. So we see that the surface temperature, very important, that temperature there, is going to remain constant. Obviously, for as long as these two bodies are semi-infinite solids. So as long as this temperature inside the body and that temperature inside the body remains constant, that surface temperature is not going to change as a function of time. It's going to be a constant. Okay? And we can see it depends quite a lot on the different properties of the F values. So if you now look at that and the discussion we've started with previously in terms of when you walk over a tile floor or a carpet floor, or when you sit there and you feel on the wooden bench or on the steel or whatever, and it feels to you as if the temperatures are different. If you look at this equation, what does it tell you? What does it tell you? What observations can you make from it? The one type of observation that we can make from it is that if FA and FB are about the same, okay, then TS would be the average of the two temperatures. Okay, that would be the first observation. Okay. So, if the properties of the two bodies are about the same, okay, approximately, then TS is going to be the average of the two temperatures. So, if your temperature is 37, okay, if your temperature is 37 on this body, and you touch another body which is at 0, maybe ice, then the surface temperature is going to be the average between the two of you, 37 plus 2 divided by 2. That is going to be the average temperature. Okay. And it's going to remain constant for as long as you live, and as long as your temperature remains 37, and for as long as the ice stays at 0 degrees Celsius. So that's the surface temperature going to be. So that is the one possibility. Then the other possibility is, if, let's suppose, the one body, the F value, which is being determined by K, rho, and Cp, the square root of it, if that is much larger than that of the other one. Okay. So let's look, for example, at the case where it is 100. Okay. So FA is 100 and FB is about 1. So let's suppose it is 100 times larger. Then the surface temperature is going to be 100 times TA plus 1 time TB divided by 101. So the surface temperature is, for all practical purposes, going to be the temperature of body A. Okay. So body A would be the determining one in determining the surface temperature. Right. Let's do a very nice example that can actually help us to understand this much better. And the example would be you in winter. Okay. Three different scenarios. You are A, body A, okay, and for body A, your temperature is 37 degrees Celsius, okay, and your K value, your rho, and your Cp would typically be that of water. It's in your textbook, and we've done it previously, so I'm not going to waste some time to write it down. Okay, so those are the values. Sorry, I will get to that in any case later. So we are going to write them down. Okay, so that is your body temperature, 37, and let's look at the scenarios where you walk over tiles, and the tiles are at 15 degrees Celsius, okay, in your house, or over a carpet. Again at 15 degrees Celsius, and then lastly over a copper plate, also at 15 degrees Celsius. And let's look at these three scenarios in terms of what would happen with you as a person and what would be let's call it be the reaction on your body in terms of surface temperature and in terms of how much heat is being transferred. Because if we look back at these two semi-infinite solids, okay, your body is going to be at 37, and let's suppose it is a semi-infinite solid, and the floor, towels, carpet, or whatever is at 15, and it's another semi-infinite solid. And we want to see close at the surface what happens to the temperature and how much heat is being transferred for these three different cases. Right, so to make it easier, it's going to be much better to draw a table, and the table is going to look something like this. Okay, the first property that we're going to consider is that of human flesh. Okay, you as a person, A. Okay. Then we are going to call the tiles is going to be B, properties of B. Okay. Then the carpet is going to be C, and the copper is going to be D. Okay. So we need to put in A, B, C, and D. Okay. There's going to be quite a few columns here next to each other. Okay, so make some room for that, or make sure that you write very close to each other with your numbers. Okay. Okay. So the K values for the different bodies is equal to 0.623, 1.34, 0.039, and 401. Okay. Thermal conductivity in watts per meter Kelvin. For water, about 0.623. For the tiles, 1.34. The carpet, 0.039. And the copper, 401, because it's a good conductor. Okay. Right, now the densities. The density of the water is about 1,000 or 996 if you want to be exact. B, which is the tiles, is 1,920. The carpet is 1121 and 8933 for the copper. The CP values would be equal to 4178, 790, 1420, and 385. Okay. The F values, if we go and calculate the F values, what is F again? F is just the square root of K multiplied by rho multiplied by CP. So it's elementary to calculate that. Okay. So here's the F value. Just need to calculate that from that and taking the square root. Okay. And the values would be 1,610, 1425, 249, and 37,136. Okay. Look at the relative sizes of these values. Okay. Now let's go and calculate the surface temperatures for these three cases. The first case is between the human flesh and the tiles. Okay, the body and the tile. Okay, so the human and the tile. So the temperature would be equal to FA multiplied by the temperature of A plus FB multiplied by the temperature of B divided by FA plus FB as we've derived it. Okay. 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 So FA is equal to 1610 multiplied by your body temperature, which is 37 if you're healthy, plus 1425 multiplied by the temperature of the tiles, divided by the sum of FA plus FB. Okay. And before we do the calculation, let's look at the relative sizes of those two terms. They're about the same order of magnitude. Okay. So the surface temperature is going to be 26.7 degrees Celsius. So your feet is going to feel a temperature as if it is 26.7 degrees Celsius. And let's write it in here, 26.7. Okay? Yep, question there at the back.
That temperature, is that the initial temperature you will feel when you step onto the tile, like instantly?
That would be the temperature that would be, it would be 26.7 as long as your body temperature remains 37 and the tiles remains at 15 degrees Celsius.
If a stone plate, like hot plate, like at 200 degrees and I touch it, it's not, I'm not going to feel 200 degrees, I'm going to feel the temperature you work out by using that value.
Yes.
I'm going to feel like 100 and something.
Yes. So the question is, yes, if you're a little bit more brave and you don't want to do this experiment, and there's a hot plate and you put your finger on the hot plate, yes, 37, and the hot plate more than 200, the surface temperature is not going to be 200, it is going to be in between. Okay. And it would actually be very close to this case here. Okay. So it's a very good example, and let's come back to that. Okay. So if you can just hold that for me for a minute. Okay. So surface temperature is 26.7, and now we can calculate the heat flux, which is equal to Ka multiplied by Ts minus the initial temperature divided by the square root of pi alpha A multiplied by T. Okay. And the T, now we have to decide when. So let's suppose we decide on 5 seconds. Okay. So what will the temperature be? The heat flux, not the temperature. The temperature remains constant. The heat flux after 5 seconds. So if we do that calculation, it is equal to 4.27 kilowatts per square meter. Okay. So the heat flux, it is 4.27, okay, 4.27 kilowatts per square meter. And now, remember, the heat flux is equal to the heat transfer rate divided by the surface area. Now, yes, every one of you, your surface area for your feet are different than that of somebody else. But let's suppose it is about 0.020 square meters, which would be sort of an average. Then we can calculate the heat transfer rate as 85 watts per foot. Okay. So for both of them, it would be about 170 watt for both your feet. Okay. So the heat transfer rate is about 170 watts. Right. Now we can repeat this problem for the human and the carpet. Okay. And again for the human and the copper. Okay. 3 different possible scenarios. Okay. And the calculations are elementary. Just follow the same recipe. So, for the carpet case, the temperature, surface temperature is going to be 34.1. Okay. So obviously that's the reason if you walk over the carpet you would say it is warmer than the tiles. The temperature of the tiles are 15, but the temperature you feel would be 34. And that is why you would say it is warmer. Right. Sorry, ladies and gentlemen, I wrote it the wrong column. All this should just be one down. Okay. 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 So this surface temperature is between A and B. Okay. So 26.7. Okay. So this is now empty. These columns. Okay. Because now we look at between A and B, between A and C, and between A and D. So that is 26.7, and it was 4.27. It was kilowatts, and the total heat transfer rate was 170. Right. For the carpet, it is 34.1. Okay. If I can just give you a few seconds to correct what you should have corrected. Are you all with me? Okay. And then the heat transfer rate is only going to be 1.18 kilowatts per square meter. What does it mean? It means that if you walk over the tiles, the heat transfer rate is 4.27 kilowatts per square meter. When you walk over the carpet, it is just 1.18. So it's almost 4 times lower, the heat which goes out of your body. And the total heat transfer rate would be 47.2. Okay. Now, the copper. The copper, and take note, and this is the important thing. And this is why this problem has been selected very specifically. Look at the big value of F. Look at the big value of F. Okay. So the big value of F, in terms of the question, where you put your finger on the stove, in terms of your question where you put the finger on the stove, look at the big F value. If you do the calculation now, then this surface temperature is going to be 15.9. Okay, 15.9. The heat flux is going to be 8.57 kilowatts per square meter, and the total heat transfer rate is going to be 342. Thus, in terms of the question of the hot plate, which is at a temperature of, I don't know, 200 and something, let's suppose 200 degrees Celsius, here's your finger at 37 degrees Celsius, okay? The F value for your finger is going to be 1610. The F value for the plate, copper or steel or whatever, is going to be about 37,000. Okay, so if you touch there, then the surface temperature you're going to measure or feel is going to be approximately 200 degrees Celsius. Okay? You've got it? Yes, question.
Sir, the relative size of the plate and the finger, can you treat them as a semi-infinite body?
Okay, that's a... Okay, so the very good question is now the relative sizes of the plate and the finger. Coming back to our derivation in terms of assumptions. Okay, our assumption for a semi-infinite solid says that this temperature and that temperature must remain constant. Okay, so yes, if you do that with your finger, after a few minutes, I'm sure your body is not going to be at 37 degrees Celsius anymore. So the calculations that you're going to try to make is not going to work anymore. Okay. So the calculations can only work, and that is coming back to the size of the bodies, if those two temperatures can remain constant. And that is the answer. Any more questions? We're not finished yet. We're not finished yet? Okay. Any more questions? None. Okay. Let's look at another example. Okay. And I think many of you will be able to associate yourself with it. Right. And that is when you jump into water. Okay. And now the water temperature is 15 degrees Celsius again. Okay. Now, who of you would like to do it? 15 degrees. Okay. Okay, so 20, Yeah, maybe many of you, maybe 25. I'm sure most of you would say, yes, I will do that. So all of us have a temperature where if you would jump into the pool, you would say, you know, it's not for me. Don't want to do any swimming. So let's look at that. Okay, so here you are, again, body A. And here's the pool. Obviously not to scale. So body A, and again, because the water for both of them are approximately, the body is 80% water or whatever, and that's water. So the two F values, would be about the same. Okay, so the F, let's call it of your body. Okay, maybe let's make this a B. Let's make it a B. Okay, and the F of the pool, they would be about the same, right? And your body temperature, the inside 37 and that one 15. Okay. So if we look at this example, then everything is still valid in terms of the calculation of the F values. Okay, we can still use them to save some time. So the heat flux would be about 4.605 kilowatts per square meter. And the heat flux, as you know, is equal to the heat transfer rate divided by your surface area. Right, now this value is equal to 4.605 multiplied by 10 to the 3 is equal to the heat transfer rate. Now, the surface area. Okay, now each one of you must decide on your own surface area. Okay, and yes, it can be a very sensitive thing, but let's suppose you are very skinny. You are very skinny, and your surface area is approximately 0.5 square meters. Okay, then the heat transfer rate out of your body would be 2.3 kilowatts. Okay, while if you're not so skinny, and let's suppose your surface area is about 2 square meters, okay, then the heat transfer rate would be 9.2 kilowatts. Okay. So the heat transfer rate of a bigger person would be much smaller, or much higher than that of a very skinny person. So what can you learn from it? Okay. What you can learn from it is you can't get children out of a swimming pool. Okay, small children, you can't get them out of the pool while the adults would long already be out. Why? Because the heat transfer rate out of their bodies are just so high. And yes, if they, at last, when you get them out of the pool, you have to do what? You have to get them in a warm bath and you have to give them food, for obvious reasons. They're very hungry. Okay? Any questions, ladies and gentlemen? Right, if not, thank you very much, and then I'll see you again next week. Thank you.